In this video, we are going to learn the what we call the DI method or the tabular method for integration by parts. So it is the DI method, or what we also call the tabular method. Tabular method for integration by parts. Integration by parts. Okay, so we can start with some notations first. So the notations. So there are two notations. So we can use f bracket n as the nth derivative. Nth derivative of f, and then g to the negative n. When we say the negative, that means the integral. We can use the notation, the nth integral of g. So we can use that notation. So if you put the parenthesis n, that means the nth derivative. When you say parenthesis negative n, that means nth integral. So we can use that difference as the derivative and the integral. So we repeatedly take the derivative and repeatedly take the integral. So let's look at the our standard integration by parts formula. So let's look at the integration by parts formula. So we know that it is the u dv equal uv minus v du. So and that's also what exactly happened here. You can see that here we have the u function and then we take the derivative. So that's a derivative part. So we take the derivative. Take the derivative. And then what happened to the other function? We start with dv function, and then you can see the v means to take the integral. So you take the integral here, and it's the same thing. So integral. So that means here what we did, we take the integral. So we integrate. So that's basically happened. So one function you take the derivative, the other function you take the integral. So if you use two functions fg, so this is what's going to happen now. So let's say you start with two functions f and g. So that's the two functions, and you integrate that. So according to this formula, what's going to happen, you can see the first function you write it as it is according to the above formula, and the second function you integrate. So it is the g negative one because you integrate once, and then there's a minus sign, and the same thing here you have the you take the derivative of the first function. So if you take the first derivative and the second function you integrate. So that's what happened in the first step if you integrate once. Now what we're going to do, we're going to apply this same formula again to the second integral. So that means if you do that again, it is f g to the negative 1 and the negative. Now let's do it again. So if you do it again with the two functions, the first one you write it as it is, the first function. Second function you integrate, that means it's going to be g, it's a negative 1, now we got negative 2. And then minus sign, and then what you do, you integrate the first function, so that means f2, and you integrate the second function, negative 2. So you can see that inside the integral, it is always the same. See the 1, 1. Here you can see 1, 1. So let's notice these things. So you see 1 and 1. 1, negative 1. Here you see 2, negative 2. So we see that pattern here. See 1, negative 1, 2, negative 2, like that. So that means if you expand this, you can write it like this. So I'm going to expand this and write this as a formula. So what's going to happen? It is f g negative 1, and then there's a negative sign, and then we have f, the first derivative, and then g to the second integral. So you see that so start with 0, negative 1, and then 1, negative 2. So we're going to keep repeating it. So if you're going to take more and more integrals, what's going to happen is you can see the sign change, and then the first one you repeatedly taking derivatives, the second one you repeatedly taking integrals. So that means it is a negative 1 n, because that's the n many step. You can see if you integrate once, you get one negative sign. if you take 2, you can see there are 2 negative signs, so negative negative become plus positive. Okay, so like that. So that means here what's going to happen as a formula, you're going to see this is f, the nth derivative of the first function, nth integral of the second function dx. So that's what happened according to the observation. So now what we can do, we can write this as a formula. And also we notice one thing, if the f function, so let's write it. So this is another observation. If the nth derivative, if f the nth derivative of the first function equals 0, what will happen? The integral going to be 0. Okay, then the process end. The process end. So you can see the process ends. So we can see that, because if the nth derivative is 0, so the process is going to end there. That means you're going to get the formula. Okay, so and then you can use this idea. So what you can do, you can use the fg function and start with the plus sign, take the derivative of the first function, take the integral of the second function, take the derivative of the first function, take the integral of the second function. Just keep doing it until the derivative of the first function is 0, then you can stop right there. So you can use that as a formula. Okay, so that's the idea. So I'm going to write those both formulas in the next one. So let's say, so the one idea was that so if we know that the nth derivative gonna be 0 at some point, if you know that, then what we can do, the integral is fg dx equal, so what we can do, we can start with the first function and integrate the second function, then minus take the derivative of the first function, integrate the second function again, and then plus take the derivative of the first function, integrate the second function again. So so keep doing it until you get a 0. So that's one formula. So you can use this as a formula, and then you can end whenever you get a 0 for the first term. And then let's try the what we call the DI method. So what's the DI method or the tabular method? Tabular method, or what we call the DI method, or what we call the tabular method. Tabular method. So what's gonna do? We're gonna start with the derivative function, and then we're gonna start with the integral function. So we're gonna start with f and g. So one of the thing is that we need to figure out what you're gonna pick for f. That's very important, because we're going to pick the function for f, so that once you take the derivative, it is simpler than the original integral. It is simpler than the original. That's how you're going to pick the f function. Okay, so let's say you pick that, and then what you do, you take the derivative. So you can take the first derivative and the first integral, right, and the second derivative and the second integral. So we're going to keep doing it, and then let's say you're going to stop. You can stop at any moment. Let's say you're going to stop at the nth derivative, and then you have the nth integral in this side. So what's going to happen now? The interesting part is, so that's the tabular we create. We start with the f and g, take the derivative of the first one, that's the d, take the integral of the second one, that's the I. Now what we can do, we're going to multiply them diagonally. So you're going to multiply f with g negative 1, and then this with that. So that's how we're gonna multiply. So you're gonna multiply them diagonal, and then you're gonna get there. And also the last step, you can write it like that. So what's gonna happen is, you always start with the plus signs. It's very important, and then switch the sign, minus, plus, like that. So the last one is always negative 1 to the n many, negative 1 to the n power, because we did n many derivatives. Okay, and the top one has to be negative 1 n minus 1. So according to that, so this is the next one. So it's a negative 1 to the n minus 1. Okay, so that is what we call the tabular. And then what we can do, we can write them as we did before. So our integral gonna be, so now the integral is. So we're going to write the integral now. So integral going to be f g dx. This equals to, you're going to multiply the first f with g inverse. So we're going to multiply according to this and then add them. So that means we're going to multiply the plus sign. We're going to multiply f with g to the negative 1 and then minus f the first derivative g to the negative 2 and then plus f to the second derivative g to the negative 3, like that. So we're gonna keep adding like that, and then at the end you're gonna end up with negative 1 to the n, the integral of f to the nth derivative times g to the negative n, that means an nth integral of dx. So the interesting part is, if this term is 0, if this is 0, then you're gonna get the expression. Okay, so if this is 0, then you get expression. So let's try to do several examples just to learn the method. So it's very easy. Again, what you do, you start with f and g, you take the derivative of the first set, you take the integral of the second set, and then what we can do after we do that, we're going to multiply them diagonally, starting with the plus sign until you get the last term. If the last term is not equal to 0, then you get an integral. If the last term is 0, you get expression. So let's look at several examples. So let's see this one. Okay. So example 1, let's say integrate let's start with something easy. So I'm going to call it a. So it is the integral of x e to the x dx. Let's look at this integral. So this is like kind of common integral, and you know that this integral you have to do using integration by parts. The substitution does not work for this problem. So what we can do, we're going to make the table now. So what's the table? So we need to start with the d and the I. So you need to figure out what's going to go with the d, what's going to go with the I. So what we normally do is we're going to pick a d so that it is, once you take the derivative, it is simpler. So that means in this case it's clear that you have to go with x as the d function and then ex as the I function. Okay, so we take the derivative. So this step is done. So we take the derivative and then we take the integral. We take the derivative and we take the integral. So that's what happened. So and so that's done because you get a 0. So that means a process is going to stop. Now what we can do, we're going to multiply them according to the along the diagonal. So we're going to multiply diagonal like that and diagonal like that, and that's it, because the last term going to be 0. So that means this is a plus sign, this is a minus sign. So that means your answer is, if you start with the first product, it is plus x ex and the minus 1 ex. Now we add the c. So that is the formula. Okay, so you can see that it is very quick, and you only need the table and you get the answer. So and we need this later in this differential equation course as well. And also I'm going to recall a formula that we don't need for this one, but if you want to integrate a e to a kx function, and how we going to do this? So if you integrate e to the kx, it's normally, if the k is a constant, it is 1 over k e to the kx plus c, e to the kx plus c. And you can also find this in the 4 formula video. So 4 formulas. So look at the 4 formula video, and you can find all those related formulas there. 4 formulas, those are very important. Sometimes we call FF for formula. Okay, good. So let's do one more example. I hope this is very clear. So let's do example number 2 with the trig function. How about we can integrate x sine 3x dx. Again, so after you get the integral, you want to figure out which one you're going to pick for d, which one you're going to pick for I. So in this case, it is clear that you have to pick d as this one and integrate this one, because the whatever we pick for d is the one is when you take the derivative, it is simpler. So that's the argument. So let's write it as before. So we have the d and the I. So d is x, and then we write sine 3x. Okay, so once you take the derivative, this is 1 here. Okay, what is the integral of sine 3x? So you can do this kind of problem using the substitution method, but there's a formula again. So what's the formula? So we know that if we have sine k is a constant, kx, so it is going to be negative 1 over k cosine kx. The reason is, and plus c. The reason is, once you take the derivative, you get a k, and the k, when you write a 1 over k, k get cancelled, so we can get like that. And also, if you integrate the cosine kx, you're going to get 1 over k sine kx. Again, the same argument. Once you take the derivative, sine become cosines, 1 k get cancelled. Okay, good. So we can use these two now. So that means our table now, if once you take the integral of sine, so it's going to be negative 1 over 3 cosine k 3x. Now take the derivative again. So it's a 0 here. Now once you integrate cosine according to the formula is 1 over k, that means you are divided by another 3, so that means negative 1 over 9 sine 3x. Since we have a 0, there's a stop here. So now let's try the formula. So we're going to multiply them diagonal. So we're going to multiply this with that and this with that and add them. So it is a plus and a minus. So that means your formula is, according to the argument, according to the tabular, so it is negative equal. Start with a plus sign, but there's a negative sign here, negative 1/3. We normally write the numbers first, so it is negative 1/3, and then we have x, and then cosine 3x. That's the first one. If you go to the second one, there are two negative signs, so it becomes plus, and so it's become 19 sine 3x, and at the end we can add a c because this is a integration problem. So you can see that that's the answer. Okay, so good. So let's do a little complicated one. How about this one? This is example number 3. You will really like it. We use this technique here rather than the regular method. So I'm going to show you a few things here. So it's a x squared minus 1 e to the negative 4x dx. So if you use the regular partial integration by parts technique, it can be a little lengthy. So let's see how things gonna work here. Again, we pick this one as the d function because once it is there is simpler, and this is the I function. Okay, and if we switch the order, it's not going to work for this problem. It's going to be more complicated. Okay, so let's start with the tabular. So we have a d and the I. So we can write x squared minus 1 here, and this is e to the negative 4x. And we know how to take the derivative. Versus the derivative, this is going to be 2x. Integral, we talked about this formula before in the previous problem. If you have e to the kx, we can divide by k. So that means the answer is negative 1 over 4 e to the negative 4x. Take the derivative, so it's going to be 2. When you integrate, you're going to divide by again by negative 1/4. That means it's going to be 1 over 16 e to the negative 4x. It's not 0. So take the derivative again, so you're going to be 0. Once you take the derivative here, you're going to be negative 1 over 64 e to the negative 4x. That's what you get. So we get 0, that means just a stop. Now we're going to multiply them diagonal. So let's multiply them diagonally. So we're going to multiply these first, and then these two, and then those two. Okay, so we start with the plus sign, minus sign, plus sign. Good. So we can write the formula now. So the answer is, you can see, equal. We're going with a plus sign, but there's a minus sign there. We now write numbers first. So when you multiply those two together, so what's going to happen? Negative 1/4, negative 1/4 x squared minus 1 e to the negative 4x. That's the first. So multiply the two and multiply by the sign. That's the first one. Second term, minus and multiply by 2 with 1/16, so that means negative 1/8 x e to the negative 4x. And then the last term, when you multiply the 2 and negative 1/16 get cancelled, you get negative 1/32 e to the negative 4x plus c. So that's the answer. So that's perfectly fine. If you can simplify this a little bit, but this is all completely fine. But if you want, you can simplify. Let's see how we can possibly simplify this one. What I normally do is I'm going to take the common denominator. In this case, it's 32 with the negative sign, so it's going to be negative 132. And write what you get. So 32, that means 8 is missing, so it's 8 times x squared minus 1. This is 32 and 8, so 4 is missing. We already take the negative sign out, so it is 4 x, and then here negative 32 you took out, so that means just plus 1, and then also at the end you're going to get negative 4x plus c. You can simplify this a little bit, so you're going to get negative 132, you're going to get 8x squared plus 4x minus 7 e to the negative 4x plus c. So that's the answer, and you can see that this you can do really quickly compared to the long process. Good. So let's see what if this never ends, because you can see that all these problems you get a 0. So now let's see what if never ends. Okay, so what if this process never ends? One such good example would be, so I'm going to do this as example number 4. Let's try to integrate ln x. Remember this ln x integral? So this is a special situation because we know that for this type of problems we normally pick the log function as the derivative part. Okay, so and here you can see that you cannot really see the v function, the second function, so we can rewrite this. So I'm going to rewrite this one as ln x, and you add a 1 dx just to make sure that is visible. Now what we can do is, so that's the function you're gonna take the derivative, because once you take the derivative, log become 1 over x. It's much simpler, and this is the one you're gonna integrate. So we can create the tabular now. So the d and the I. So once you write the two functions ln x and 1, if you take the derivative of ln x, it is 1 over x. If you integrate, this is going to be x. So once you get a polynomial, you can stop right there because it's easy to integrate now. So let's see what we get. So we only have one term here, so we're going to start with the plus sign now. So let's write what we get. So you're going to multiply the two functions and with the sign, so that means you're going to get x ln x, and then here we did not get a 0, so that means we're going to multiply this way. When you multiply that way, it is a plus and a minus. You see that it's a minus, so it's a minus. You're going to multiply these two. So we're going to get the minus 1 over x times x dx. This is very easy to simplify. simplify and you get 1, so that means you're going to get x ln x. Integral of 1 is x plus c. So that's what you get when you integrate ln x. So it's coming from the di method as well. Okay, so good. So let's do a little complicated one. So how about this one? So we can do a little complicated problem. So let's see example number 5. How about you do x3 ln x to the whole thing squared dx, something like that. Okay, and then you can see that when you see log functions, we normally pick that as the d function. That means this is the d function we're gonna pick, and that is the I function. Okay, because once you take the derivative of a log function, it's gonna be end up with a polynomial at least 1. Okay, so let's write the d and the I. So we have ln x squared, this is x to the third. Once you take the derivative of this function, used by the chain rule, it is 2 ln x times the derivative of the inside function. Inside function ln x, so the derivative of that is 1 of x. So that's what you get as the derivative. And if you integrate the other function, you get 1/4 x to the 4th. So what we can do, so this is simpler, and you can see that even if you now, let's say you're going to keep doing this, but if you keep doing it, you can see that the ln x function never going to stop, because ln x appear because it's going to be a product. So in the product rule, the ln x function going to appear. Then if you take one more derivative, it's going to be more complicated. So because of that, we are not going to do that. We're going to see what's going to happen in this case. So let's again write the answer according to these two. So we have plus and a minus. The sign change plus minus. So let's write what we have now. So if you look at those two, you're going to get 1/4 and then x to the 4th, and then we have ln x squared. That's what we have. We assume that the x, we take the absolute value sign. Okay, minus, there's a minus sign, plus minus. You're going to multiply the two. When you multiply the, you get 1/2. And then what's the integral going to be now? So integral going to be, it is ln x, we have 1 of x there, and we also have x to the 4th. Okay, so you can kind of simplify this one now. So we're going to see 1/4 x to the 4th ln x squared minus 1/2, and then you can see x get cancelled, so you're going to end up with x3 ln x. So you can see that this is actually better than the original one. In the original one, you had a ln x squared, but you don't have it anymore. Now what we're going to do, we're going to do this integral again using the tabular method. So that's what we're trying to do now. So we use this again, the idea. So let's do it. So that means we have a new tabular now. So in this case, so this is again the d function, and this is the I function. So let's make another table for that. So we have a d and I again. So the d is ln x, I is x3. Take the derivative 1 of x. Take the integral 1/4 x to the 4th. Now again, as before, we're going to multiply. We're going to stop here because you get a polynomial, so you stop. So we're going to multiply this with the plus sign, multiply that with the negative sign. So that means your next step going to be, so I'm going to write them here. So it is 1/4 x to the 4th ln x squared minus 1/2 So let's try the formula, what you get here. So you're going to multiply the 2, so that means 1/4 x to the 4th ln x, and then the minus sign, you have a 1/4, and then the integral of the product, so it is 1/x to the x/4 dx. We can simplify this a little bit. So if you simplify, you're going to get 1/4 x to the 4th ln x squared minus, you can multiply this, and you can see that so we have a so we have a 2 and 4, so it's a 1/8, and then we have x to the 4th ln x that we have, and then negative negative positive, so it's going to be 1/8 again here, and then the inside here is going to be x3 dx. That very easy to integrate. So once you integrate, as the final answer, you're going to get 1/4 x to the 4th ln x squared minus 1/8 x to the 4th ln x, and then plus 4, so that means you're going to get a 4 there, so 1/32, and then you're going to get x to the 4th plus c. So that's the final answer. If you want, you can factor x to the 4th. You can see x to the 4th is everywhere, and also 1/32, but yeah, this is also fine. You can leave it like this. Okay, so that's the kind of idea. So you can see that you can also do like complicated problems like that, but in this case you have to do the integral twice. Okay, because if you try to do it with the first integral alone, that's not gonna work, because you have the product rule, that the product never gonna go away. So that means ln x is gonna stay there, and it's gonna be more complicated every time you take the derivative. So it's better to kind of stop the integral right there and simplify and see what you get, and then do it again. Okay, so let's do the final integral. So one of the celebrated integral in physics and chemistry. So we're gonna do that one as the last example. So you may remember we have the integral that involve e and sine or cosine function. So that's what we're gonna do. So let's try to do it and see what's gonna happen. So it is e to the, let's say e to the negative 2x sine 3x dx. Okay, so e to the negative 2x sine 3x, and you know that if you try to do the regular way, you know you have to do this twice. You have two integrals, you have to integrate twice and then combine, things like that. But with this method, you don't want to do that. You can do it in one. Okay, so that is one of the benefit of this technique. Again, so here the problem comes like which one you're going to pick as d and I. So in this problem, actually it does not really matter. You can pick anything you that you like. Okay, so but I am going to go with this as the d and this as the I integral. But even if you switch the order, it still work. At the end, you get the same answer. Intermediate steps might be different. Okay, so we're going to start with the d and the I. So so we have e to the negative 2x, and then we have sine 3x. So we take the derivative, so that means it's going to be negative 2 e to the negative 2x, and we take the integral. This is sine, so that means it is negative 1/3 cosine 3x. Take the, so you can see that it changed, but you don't see anything yet. Now we take the derivative and the integral again. So we take the derivative, multiply by negative 2 again. That means it's going to be 4 e to the negative 2x, and then integrate. It's a cosine, that means sine, so you can divide by 3, so that means a negative 1/9 sine 3x. Now the question, are we going to keep doing it? But you can see that except the coefficients that you have, the multiplication factors you have, you kind of end up with the same two functions that you start with. So that means this is a good place to stop. So we can stop the taking di at this step. So let's see what we get now. So as before, you're going to multiply these two, and then you multiply those two, and also you're going to multiply these two. Okay, so we start with the plus sign, minus sign, plus sign. So let's write what we get now. So if you write what we have, so we start with the plus sign. There's a negative sign already, so that means negative 1/3 e negative 2x cosine 3x. That's the first term. The second term have three negative signs, negative, 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 so that means be negative. Multiply the two numbers, you're going to get 2/9. And then the functions, it's going to be e to the negative 2x, and then we have sine 3x. Now if you multiply the last one, you get the integral. So what's the integral? It's a plus sign, but with the negative sign there, it's very negative. So it's going to be a negative 1/9. The integral of e to the negative 2x sine 3x dx. Now, so what you can see is, and also actually there's a 4, so we forgot the 4. So, and the 4, there's a 4. So we multiply the numbers, you're going to get 4 negative 1/9. Okay, now what you can do is you can see that this integral is exactly the same as the integral that you start with, except the number. So because of that, you can move this integral to the other side. Okay, we're going to move that term to the other side, adding that term to the both sides. So that means we can add the same term to both sides with opposite sign. That means you end up getting plus 1 plus 4/9, because you add the two integrals, and then you just write one integral, negative 2x sine 3x dx. On the other side, what we have is negative 1/3 e to the negative 2x cosine 3x minus 2/9 minus 2/9, and you can see e to the negative 2x sine 3x. We are not going to add the c yet, we're going to add the c at the end. So now you can see this is simply 13/9. So what we can do, we can multiply both sides by 9/13 upside down, so then they cancel. So that means you're going to get as e to the negative 2x sine 3x dx equal, so you're going to multiply by 9/13. If you multiply by 9/13, you're going to end up with negative 3/13 e to the negative 2x cosine 3x minus, if you multiply by 9/13, this 9 get cancelled, so you're going to get 2/13 e to the negative 2x sine 3x. But you can see that for these kind of problems, the e term is always common, so I'm going to take it out just to make it simple. But this is all completely fine, but if you want to simplify, you can say negative 13 you can take out, and also e to the negative 2x you can take it out, and you end up getting simply 3 cosine 3x, and then plus 2 sine 3x, and then you add the c now. So that is the answer to the problem. But you can see that this is not as complicated as the standard method, because in the standard method this can be a little complicated because you're going to get a lot of terms, but you need to understand where to stop the tabular. You're going to stop the tabular right after you see the same product. So once you see the same product, you can stop, because then you're going to get the same integral, you can bring it to the other side. Okay, so we did several examples. Now I'm going to give you several practice problems, and you're going to see the answers in the description. So let's do a few examples. I'm going to give a few practice problems. Okay, so I'm going to say practice problems. Practice problems. So I'm going to say exercise number 1. let's do x minus 1 e to the x dx. Little easy one to start with. Number 2, we can do x squared plus x minus 2 with e to the negative 3x dx. Just imagine if you want to use a regular method for this one. Number 3, let's say x plus 1 cosine x over 2. Be careful, we have fractions now, okay? But since we have the shortcut formula for integrating cosine kx, so we can do this. And the number 4, we have x squared minus 1 ln 3x dx. And number 5, we have e to the, let's say 1 minus x. How about that? Cosine x over 4 dx. Okay. So try to do these problems and you can match your answers with the answers in the description. So thank you so much for watching.